Alright, hello class. Today we're moving on to 4.8, which is actually sort of a new topic. I'm not really sure why it's put in chapter 4. It should really be kind of lumped into chapter 5, but this is on the subject of antiderivatives. Okay, what an antiderivative is, it's basically we're taking the idea of the derivative and going in the opposite direction. So if we start with f of x, and we know we get to f prime of x using the derivative, okay, that's one direction. But in math, like everything else you've ever learned, you always learn the opposite direction to get you right back to where you started. Think about it, if I know how to drive home, right, or if I know how to drive to work, I could drive to work, but if I didn't know how to get back home, let's say it was all one-way streets, I'd be pretty pissed, right, because I couldn't leave. I'd be stuck at work forever after that point. Same is true here. We know how to get from f to f prime to the derivative to the rate of change, right, by differentiating. Antiderivatives attempts to answer this question. Well, how do we get back? Say we have the derivative and we go back to f. Okay, and that comes from what is called the antiderivative. There's also another name for it, integral, which we'll start using as well. But let's start with the definition of the antiderivative. So here we go, off to the side here, a function capital F of x, that's often what we use for the antiderivative. So this function capital F of x is an antiderivative of little f of x if capital F prime of x is equal to lowercase f. So if we take the derivative of this capital F, it gives us little f, then this capital F is an antiderivative of little f. So for example, to kind of show what's going on here, let's say little f of x is equal to 2x. Okay, and I want to find an antiderivative of that. So can you think of a function that, so what we're really looking for is a function when we take the derivative. Okay, so we want capital F to be such that capital F prime of x will give us 2x. So can you think of anything out there that when we take the derivative of it, we get out 2x? And the answer, of course, is x squared. Okay, so capital F of x equal to x squared is an antiderivative of little f, which again was 2x. Okay, so you kind of have to think backwards here. You always have to think, okay, what function, when I take the derivative of it, will give me 2x? So x squared is an option because capital F, right, since capital F prime would be 2x, which is little f. Okay. But, and one of the unique things about antiderivatives that kind of makes them interesting is that the x squared is an option, but notice that x squared plus 1 is also an antiderivative of little f of x, right? Because when we take the derivative of this, the derivative with respect to x of x squared plus 1 is 2x. Plus 0, of course, because the derivative of a constant is 0. So x squared plus 1 is also an antiderivative of 2x, as is x squared plus 10, x squared plus pi, x squared minus 13, etc. Right? So this brings up a really interesting idea, or a really interesting concept of the antiderivative, is that so an antiderivative is not unique. Right? Antiderivative. That's why I actually say an antiderivative instead of the antiderivative, because for each function, say 2x, it has a countless number of antiderivatives. But they should all follow the same pattern. They should all be basically x squared plus a constant. All right? So there are countless antiderivatives for little f of x equals 2x. Okay? But they all must look like x squared plus a constant. And we can only add in a constant, because if we add something else in, say if we added in another x, like x squared plus x, the derivative we would get would be 2x plus 1, which is not what we started with. Okay? So this will bring us actually to what I like to call the antiderivative. Okay, so I'll hit up that definition right now. Okay, so the family of antiderivatives. So if f of x, or capital F, is any antiderivative of little f of x, then all of the antiderivatives, okay, of, I should say little f, have the form capital F of x plus c, where c is an arbitrary constant. Okay, so I like to call this the antiderivative. So find the antiderivative of, say, little f of x equals 3x squared. Okay, so what we want is we want a capital F of x where capital F prime of x will equal 3x squared, right? So we want a function whose derivative will be 3x squared. So give that a think. Okay, what do you think? What function would give us that? The answer is, of course, x cubed. And then to get every antiderivative, it's going to be x cubed plus c, plus any other constant, right? Since the derivative with respect to x of x cubed plus c, that will be the derivative with respect to x of x cubed plus the derivative with respect to x of c. Derivative of x cubed is, of course, 3x squared. That's what we want. And the derivative of a constant is 0. So it's 3x squared. All right? All right, so let's introduce some notation that's going to make this a little easier to talk about. If capital F is an antiderivative of little f of x, then the indefinite integral of f of x is talked about in this form. Okay, and here's what this symbol means. This is an elongated s, right? It is supposed to be an s. It stands for sum, but this means the indefinite integral of, okay, so this we call the integral symbol. And actually, for indefinite, we usually drop the word indefinite. There is a definite integral, but usually I just say definite when I mean definite, and integral when I mean indefinite. But basically, the integral of, all right, that's what this symbol means. And then we have, of course, f of x. and this is the differential of x. Right, so the differential. Remember we looked at that a couple sections ago. Now where do these symbols come from? Well, we will answer that in probably section 5.2, 5.3. There's a reason why we use this s for sum, okay? Because basically the antiderivative is very closely related to a special kind of sum. All right, but we'll get into that later. What we really need to know for the this is that this is essentially the antiderivative of little f of x. Let me shift that over so you can see. Right, this is the antiderivative. So this is just a better way, a quicker way to write. You know, I can now like use this notation instead of asking you what is the antiderivative of blah, what is, you know, all that. I can just say, hey, like the previous example, the integral of 3x squared dx, we found that that was x cubed plus c. All right, it really simplifies the way we talk about this stuff. So that's what you really need to know. So the term integral and antiderivative are interchangeable. Okay, I'm going to try and use antiderivative as much as I can in this case, but you'll hear me say integral a lot, and they mean the same thing. Okay, and we'll get to that a little later, why that's true and how they're related. All right, now we're going to try and establish some integral rules like we did with derivative rules, right? And we can always just think backwards, but it actually starts to get kind of difficult when we do that, when things get a little more complicated. So let's just start thinking about maybe setting up some rules for us. For example, let's start very simply. Let's say I have the integral of a constant, maybe 5. Okay, we'll start with an actual constant. So what's the antiderivative of 5? So basically we want, remember we want a function capital F of x where capital F prime of x will be 5. Now think about that. What do we get? We end up getting 5x, and not just 5x, but 5x plus c. Okay, so if I have any constant, let's just say k dx, right, the integral is going to be kx plus c. I would have used c, but since I use c here, I didn't want to confuse things right off the bat. But there you go. Okay, we could always use d or e or f or whatever we want for our arbitrary constants. All right, so there's the integral, or the antiderivative of a constant is the constant times x plus c. We could call that the constant rule if we want. Right, so different than the derivative rule for a constant. The derivative of a constant is 0. The integral of a constant is the constant times x plus c. Okay, let's try the integral of x dx. Okay. So the integral of x dx, well, right, we want, remember, this is always asking a very specific question. We want capital F of x where f prime of x will be x. So give that a think. All right, we want to end up with x when we take the derivative. So we definitely need an x squared, right? The first thought a lot of people have is, how about x squared, right? Because when you take the derivative of x squared, it will become an x, but that's not good enough. That when we take the derivative of x squared, we get 2x. We didn't have a 2 here. So what can we throw in to get rid of that 2? Well, what we actually do is we put in a 1/2, because 1/2, if I throw that in as a constant, when you take the derivative of 1/2 x squared, capital F prime will be 1/2 times 2x, right? And the 2's will cancel and we'll be left with just x. So the antiderivative of x is 1/2 x squared. And then plus an arbitrary constant, right? That takes care of all of them. All right, so there's that. Let's take another step forward and look at the integral of x squared dx. Okay, so x squared dx, remember we want the antiderivative of that, so we want a function capital F of x. When we take its derivative, okay, where capital F prime of x is going to be x squared. So of course x cubed is a good thing, you know, a good way to start, but when we take the derivative of that, we get 3x squared. So what should we add in? Think about that. What should we add in to get rid of that 3? And the answer is, of course, 1/3. Okay. So if we throw in a 1/3, that cancels. We get x squared. All right, so the antiderivative of x squared is going to be 1/3 x cubed plus c. And there we go. Okay. What about the antiderivative of x cubed? What do you think? Well, if we follow the same pattern, you might think, hey, it's probably 1/4 x to the 4th plus c. And if you thought that, you'd be correct. And if we wanted to check that, right, to check, what do you think we do? Well, we differentiate. So the derivative of this, 1/4 x to the 4th plus c, we get 1/4 times 4x cubed plus 0, right? And so the 4's cancel, and we're left with just x cubed, which is what we started with. Okay, so as you can see, this is kind of like a backwards power rule, right? The pattern is we don't bring the power down with multiplication and subtract by 1. We actually go in the opposite order and do the opposite things. We add 1 to the exponent and divide by that number, right? Because the antiderivative of x to the 4th dx is going to be 1/5 x to the 5th plus c. I'll let you take the derivative of that to make sure that it's correct. But what we essentially have is this pattern here, right? And I like to call this the backwards power rule. And you'll hear me just call it the power rule because it is the power rule for integrals. So backwards power rule for integrals or antiderivatives. It's basically the power rule but backwards, right? If you want to integrate x to any power dx, right? Basically, it is x to the power plus 1, okay, divided by that power plus 1 plus c. Okay, so it does the opposite of what the power rule for derivatives does. Remember, the derivatives, you bring the power down with multiplication, then you subtract 1 in the exponent. The integral does the exact opposite. It adds 1 to the exponent, then divides by that number, right? Even in the opposite order. You'll also see this written as 1 over p plus 1 times x to the p plus 1. Okay, that's how we were writing it with a fraction on the outside. Doesn't really matter. And don't forget your plus c. And I'll say this is true provided p does not equal -1. Right? What happens when p is equal to -1? Or just think about why that wouldn't work for p equals -1. Okay, and And if p is equal to -1, that means that will work for anything except 1 over x being your integrand. I forgot to say over here, you'll hear me use that word a lot. This f of x is called the integrand. That's the thing being integrated, the integrand. So when I talk about the integrand, that's what I'm talking about, the thing being integrated. Okay, so there we go. There's the backwards power rule. Okay, from here, we can probably think of a lot of different rules that we can establish. Maybe e to the x, maybe sine, cosine, all those. So let's just knock out a whole bunch of those rules and start looking at some examples. All right, this one should be easy. What do you think the integral of e to the x dx is? So we want something whose derivative is e to the x. Well, it better be itself. Okay. All right, that's fine. What about e to like a constant times x? Right, say it's e to the 5x, for example. Okay, so remember we want a function capital F where capital F prime is going to be e to the 5x. Now a lot of people will say, hey, it's going to be itself. That's easy, right? It should be e to the 5x. But when you differentiate e to the 5x, you get 5e to the 5x, right? We don't want that 5 there. We didn't start with that 5. So what we do is just like with the power rule, or x to a power, I'm going to throw in that 1/5. So it cancels, and we get e to the 5x. So the answer, the integral of e to the 5x, is 1/5 e to the 5x plus c. So it's just like with the chain rule, the basic chain rule with derivatives, where if you had a number on the inside there, you multiply by it. What you do with the integral is you divide by it, right? So it's exactly the opposite. So if a derivative rule, I'll just say this, if a derivative rule multiplies, the integral rule divides. Okay? If a derivative rule adds, okay, the integral rule multiplies. Or, excuse me, subtracts. Okay. All right, so anything a derivative rule does, the integral rule is going to do opposite. And this does come down to just thinking backwards. Okay. All right, so basically, e, the exponential rule, let me do it here in the center, if I have e to the kx, right, a constant times x, it is going to give me 1 over k, 1 over that constant, e to the constant times x plus c. All right, so there's the exponential rule. And pretty much this can work for anything. I mean, if you have the antiderivative, capital F is the antiderivative of little f, then if you're taking the integral of f of a times x, some constant on the inside of your function, you bring it out as division, 1 over a. This is something, whenever I teach Cal 2, I see students forget to do this all the time. It's the same with the chain rule with derivatives. If you have a constant on the inside of your function, that constant comes out somehow. If it's derivatives, you're multiplying. If it's integrals, you're dividing. Okay? All right, let's think of some other derivative rules we might employ, or maybe turn backwards. Say maybe the trig functions. All right, so say the integral of sine. So we want something whose derivative is going to give us sine. So I want a capital F where f prime of x is equal to sine. All right, so you might think cosine, but if you just did cosine, okay, say if you chose capital F of x to be cosine, then capital F prime of x would be negative sine. So we actually have to incorporate a negative into it to get the answer. So the answer is actually going to be negative cosine of x plus c. Okay, and then the integral of cosine x dx, well, we want something whose derivative is equal to cosine, and that's simply going to be sine of x plus c. So as we see, since the derivative rules of sine and cosine are each other, the integral rules are too, but you see that the negative is on the other one. All right, it's the integral of sine that gives us the negative, but the integral of cosine that gives us the positive. Again, it's opposite of what we had before. Okay. All right, so there's sine and cosine. Now for the other trig functions, you might think, all right, well, how about the integral of tangent? And we need a little bit more work here because off the top of our head, we probably don't know any function whose derivative is just going to equal tangent. We kind of have to think a little bit more backwards, right? If I have the derivative of tangent, right, is secant squared of x, then instead, here's how I make the integral rule. The integral rule comes from the integral of secant squared dx is going to equal tangent x. It's backwards of what we have. Okay? And we can take that a step further as well. If I have that, the derivative, we know that the derivative of cotangent x is cosecant squared x. Okay, and we need to put a plus c in here. And that's a negative. Okay. Then I can say that the integral of cosecant squared x dx, right? If I want to get back to, say, I don't have the negative here, so I can move it over here. So what this tells me is that the derivative with respect to x of negative cotangent x is positive cosecant squared x. So the integral of cosecant squared x is going to be negative cotangent x plus c. So these go backwards. Okay, so we can't really just jump at the integral of tangent, cotangent. We'll get there eventually. There is a way to find those. That's going to be all the way in section 5.5, so that's a little ways from here. Okay. Let's look at, right, we know that the derivative of secant is secant x tangent x. And we know that the derivative with respect to x of cosecant x is negative cosecant x cotangent x. Okay, so when we make the integral rules, what we do is we say the integral of secant x tangent x, we're just going backwards, we're just mapping backwards using the integral. Okay, that will be secant x plus c. And if I do cosecant x cotangent x, this product here, its integral is negative cosecant x plus c. All right. So there's that. So there's your trig functions. What are some of the other functions we looked at in the past for derivative rules? All right, you might think natural log or a general exponential. So let's start with a general exponential. And this one's not too bad. If you have that the derivative with respect to x of b to the x, right? Remember how you take that derivative? It's itself times the natural log of b. Well, if I want to do the integral of b to the x dx, okay, and I want to find something when I differentiate it, I get b to the x, you might think the answer is b to the x, but remember, b to the x, when you differentiate, gives you an ln(b), so we need to get rid of that ln(b), right? For example, if you let capital F of x be b to the x, then f prime of x is ln of b times b to the x, so we need to get rid of that, and we do that by dividing by the natural log of b. To get back to our original b to the x. So the answer is actually b to the x over the natural log of b. So think about that. The derivative of any base to the x is itself times the natural log of the base. The integral of any base to the x is still itself, so the opposite of giving you itself as itself, but divided by the natural log of the base. Okay, so that's the general exponential rule for integrals, which basically just means that, say, the integral of 5 to the x is dx, we'll need that, is going to be 5 to the x itself over a natural log of 5 plus c. Okay, so again, this is just all thinking backwards. But I will say that if you don't know your derivative rules very well, you're not going to know your integral rules very well, because they are all based on the derivative rules, but you're thinking backwards, which is a little tougher. But at the same time, right now, this should be pretty simple because this is all basic rules. We're not to backwards chain rule or backwards product rule yet. We're not to all those crazy backwards rules. Okay? And a lot of those are actually safe for Cal 2. So this integral stuff, you are actually given a realm where you can get really good at the basic integrals because that's all you've got to focus on. Okay? And you really need to do that if you expect to do well in Cal 2. I'm warning you now. If you don't have your basic integral stuff down really well when you get to Cal 2, you're going to be screwed. That's pretty much all there is to it. Okay, so anyway, let's move on. All right, last rule you might be thinking of is natural log. Now we can't just go in, much like tangent, if I just say, hey, what's the integral of natural log, you might be hard pressed to find something. Right, because you'd want capital F where capital F prime of x is natural log. And off the top of my head, I mean, of course, I know what the answer is, but with the skills we have right now, we might not be able to just think what the integral of natural log is going to be, what that might be. And that's because the rule we have associated with natural log is, well, when I take the derivative of natural log, I get 1 over x. Right? And that goes all the way back to the power rule, where the power rule for integrals doesn't work if the power is equal to -1. When the power is equal to -1, we get 1 over x. So we actually map back to ln x. Now you might just think, oh, okay, so the integral of 1 over x is natural log of x, but we have to be a little more careful than that. Okay? For this, the domain of the natural log of x. All right, and this is getting a little subtle, something you might not have seen before, but natural log of x, this domain is only true when x is greater than 0, right? This is what the natural log of x looks like as an asymptote at 0, and it has nothing on the other side of it. Okay, but if I take a look at the derivative of the natural log of negative x, okay, and take its derivative. Remember, it's going to be derivative of the stuff, which will be -1, over the stuff, which is negative x. So I get 1 over x again. Okay, so that's interesting. So basically what we have is that that 1 over x, if I was going to find an integral rule for it, well, do I map back to ln of x or ln of negative x? Well, if whatever's in natural log has to be positive, then this thing is only true when x is less than 0. Okay, so here is the natural log of negative x. Okay, so actually, if I want 1 over x, if I want an integral rule for 1 over x, right, that exists where 1 over x does, so 1 over x exists everywhere except for 0, right? If I want an expression that exists exactly where it does, well, I can't just do ln of x, and I can't just do ln of negative x. I actually want a way to incorporate both. Okay? So we want both ln of x and ln of negative x. Okay, so let's write something here. Let's say that using this, what we've just talked about, okay, that the derivative of the natural log of x is equal to 1 over x when x is positive, and negative x, blah, 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 when x is negative. Let's think of it this way. Let's say that the integral of the natural, or of 1 over x dx, excuse me, is going to be, well, it's the natural log of x, okay, when x is positive. And I'll put a plus c. You know, you can think of the plus c out here. It doesn't really matter. And then the ln of negative x, I should say it does matter, but not for this part of the discussion. Let me verify that. Okay. And it's going to be ln of negative x when x is less than or equal to, or less than 0, not equal to. Okay. Now maybe this reminds you of something. When x is positive, we don't do anything to it. It just is x. When x is negative, we make it a negative x, which makes it a positive. So what does that remind you of when say I don't have, when the value is positive, I don't do anything to it. When the value is negative, I make it positive. Well, it should remind you, actually, of the absolute value of x. The absolute value of x is basically x when x is positive and negative x when x is negative. Okay? So, what this is essentially saying is that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. And that is what takes care of everything, because the graph of the natural log of the absolute value of x looks like this. That takes care of the whole domain, and it takes care of both cases, takes care of everything. So actually the integral of 1 over x dx is the natural log of the absolute value of x plus c. And here's a thing a lot of people forget. Okay, I see a lot of people forgetting to put that absolute value of x, but you've got to put that there. Right? You want the entire function. Okay, so that's all the rules that I can think of, other than there's some other basics, like the constant multiplication rule is still in effect. Right? If you have a constant, let's use the letter A. If you have a constant times f of x and you're integrating, you can actually move that outside and it just comes along for the ride, just like with derivatives. Okay. If you have a sum, like the integral of f plus g, we do of x, okay, f of x plus g of x dx, that's going to be the integral of f of x dx plus the integral of g of x dx. So you can do it, you can integrate like you do differentiate, where you can do it term by term, right, which is actually a wonderful boon for us when we do this. All right, so let's look at some examples, and then that'll be it for this section. All right, let's start with this example. The integral of 2x plus x to the 2/3 plus the square root of x. So once again, we're going to start by simplifying things. Remember, this has to be your first step, because basically I need this as x to a power, right? Because I want to use the backwards power rule. All right, so now it's just going to be the integral of 2x, so that 2 comes along for the ride. Now I'm going to use the backwards power rule for x, so that's x to the 1, so it's going to be x to the 2, or I'll just go ahead and write it out for this first go. This will be x to the x plus, or x to the 1 plus 1, all over 1 plus 1, okay, plus x to the 2/3 plus 1 over 2/3 plus 1, all right, plus x to the 1/2 plus 1 all over 1/2 plus 1. All right, it looks really messy in this form, but this really shows what we're doing at each step with that backwards power rule. Okay, so this is essentially x, or 2 times x squared over 2, and here the 2's cancel, plus, all right, this is going to be x, so 2/3 plus 1, which is 3/3, that'll be 5/3 divided by 5/3. That should be the same number on the top as it is on the bottom, or same number in power as it is in the bottom. Okay. Plus, now this is x to the 1/2 plus 1, so that's going to be x to the 3/2 over 3/2 plus c. Okay. We're not going to leave it like this. What we're going to do is simplify this a little bit. This is x squared, and this, when you divide by 5/3, you're basically, when you divide by any fraction really, what you can do instead is invert and multiply. So you can multiply by the reciprocal. So basically this is 3/5 times x to the 5/3 plus 2/3 x to the 3/2 plus c. And essentially, you can always do this when you have fractional powers of x. Okay? Because once you find what the exponent is going to be, here the exponent's 5/3, the constant that's going to be in front of it is 3/5. Okay? Here I know the power that x is going to be raised to is 3/2, therefore the number in front of it is going to be 2/3. It's always the reciprocal in front of the x. All right, so let's do another example that kind of utilizes that. All right, here we have the integral of x to the 1/5 plus x to the 2/3 plus x to the negative 1/2. We'll focus. Okay. So essentially, what this is going to be is x to the 1/2 or 1/5, okay, plus 1. So 1/5 plus 1, okay, is going to be 1/5 plus 5/5, so that's 6/5. So once I have this number, 6/5, I know that the constant outside is going to be 5/6. Okay, so go ahead and try it with the power rule where you divide it and invert and multiply and all that, and you always get this same thing. It's going to be 5/6 x to the 6/5. And it should make sense because if you go back to the your original power rule, let me find it here. Yeah, you're always dividing by it. You're always 1 over that power. So when you have x squared, you'll have 1/2. You take the power and multiply by the reciprocal. So doing that actually helps with the fractions here. So 2/3 plus 1, that'll be 2/3 plus 3/3, so that will be x to the 5/3. I think that was in the last example. Okay, there we go. And here, negative 1/2 plus 1/2, well, that's going to be 1/2, and the reciprocal of 1/2 is 2. Okay. Plus c. Now down here, you can always still do this as x to the negative 1/2 plus 1 over negative 1/2 plus 1, which is x to the 1/2 over 1/2, and then invert, multiply to make it 2x to the 1/2. You can do that, but I'm giving you this to save you some time with these problems. Okay, and that is that. Okay, let's look at this integral. E to the 4x plus 5 over x squared plus 4 over x cubed plus 2 over x dx. Now, this is just going to be our exponential rule. This, of course, we're going to rewrite this one using, so we can use the power rule. We're going to rewrite this one so we can use the power rule. This one is a rule unto itself, and that's the natural log rule. Okay, so I'm going to simplify what I can. This e to the 4x plus, this will be 5x to the negative 2, okay, plus 4x to the negative 3. And I'm going to leave this as 2. And actually, you can rewrite this as 2 times 1 over x, if that helps. Okay. So, we're going to just go down the line and start taking antiderivatives. So the integral of e to the 4x is going to be itself, but since we have a 4 up there and it's an integral, it's 1/4 e to the 4x. Okay. All right, then that 5 comes along for the ride, and this will be x to the negative 2 plus 1 over negative 2 plus 1. All right, I'm just writing it very explicitly here again. Then plus 4, x to the negative 3 plus 1 over negative 3 plus 1. Okay. Plus 2. Then the integral of 1 over x, we should know, is the natural log of the absolute value x plus c. So, before you ask, no, you cannot leave it like this. This is sloppy, terrible. I'm not huge on simplifying things when you don't need to, but no, you've got to take this a step further. Okay, so this is 1/4 e to the 4x plus, this will be 5 times x to the negative 1 over negative 1. So the next step, we will actually simplify that one step further. But then this will be 4 times, this will be x to the negative 2 over negative 2. So this is going to simplify down some, right? We'll cancel with the 4. And the plus 2 ln absolute value of x stays that way, and we get plus c. Okay. So finally, final step. Yes, you could skip to this one from here if you wanted, but dividing by a negative, that'll be minus 5x to the negative 1. This will be minus 2x to the negative 2 plus 2 ln absolute value x plus c. And there we have it. Okay, here's an example incorporating some trig functions, and it's going to incorporate that dividing idea, right? That if you have a constant times x in your integrand, that you're going to divide by it. Okay. Now there's no real simplification to do here. What's the integral of sine? It's going to be negative cosine of x. Okay. What's the integral of cosecant squared? Well, cosecant squared is going to give us negative cotangent. Okay. But since we have a 3x in there, what do we need to do? We've got to divide by 3. So this is going to be minus 1/3 cotangent 3x. Okay. And same thing here. Secant tangent is going to give us secant, right? But since we have pi x on the inside there, we're going to divide by 1 over pi. Okay, it's kind of a very basic backwards chain rule. All right? And there we go. And that's essentially all there is to that one. A little complicated. We incorporated a lot of things there. But yeah, so that's essentially all I want to talk about in this section, other than the fact that sometimes you will be given a problem that will say find f of x if f prime of x is equal to 2x plus 4 and f of 0 is 40. Okay, so what they're essentially doing is if f prime of x is this and you want to go back to f of x, so we can go back to our original question that started this whole section, that if the derivative takes us to f prime, it should be the integral that takes us back to f. So if I have that f prime, okay, is 2x plus 4, well, the integral of 2x plus 4, okay, is going to be, shift it over so you can see a little better, 2 times x squared over 2 plus the integral of 4 is 4x plus c. This must be our f, right? So f of x, I know, looks like x squared plus 4x plus c. Okay? Now, what this is saying is find a very specific f, specifically the one where f of 0 is equal to 40. So, if f of 0, which I know from here is 0 squared plus 4 times 0 plus c, but is also equal to 40, what that tells me is that c is equal to 40. So that we're looking for the specific f, or antiderivative, such that c is equal to 40, such that arbitrary constant is equal to 40. So our f is x squared plus 4x plus 40. Okay, so this is a very basic differential equation, for those of you who are curious. And you can think about this, you'll see this in applications a lot where this is your initial value. So say this was the velocity and you wanted to get back to the position. What this is telling you is that's your initial position. So often C ends up being your initial condition, your initial position, your initial whatever it is. Okay? Alright, so that's good enough to get you started on a lot of the examples. We'll talk next time. Cheers.